lot of people that are afraid of the cold. Well, you're not going to miss a whole lot. So today we're just going to go over the lab. There were a bunch of common misses. I want to go over those. And then I'm going to do a little video demonstration of sonic choke flow. So I'll do a video of this, and we'll wrap it up. Okay, so when I did the lab, here's what I got, folks. So pretty much everybody got this. That was no problem. The thing that I thought was kind of neat about this was, even though we put more than twice the voltage, we didn't get more than twice the temperature drop here. So a large voltage increase, a large power increase to the Peltier device doesn't buy a whole lot. And that was reflected in the COP. Okay, so to do this, the biggest thing we saw in the lab reports was people forgot to subtract off the voltage drop from the MOSFET and the shunt resistor. So the first thing I did, this is all just a gathered data, and then I subtracted A4 from A1. That gives me just the voltage across the Peltier. That was a super common problem that plagued a lot of people. So then I take this value, multiply it by the current that was coming off the shunt resistor. So that gives me my electrical power. Great, cool. Okay, thermal output. A lot of people had trouble with this one too. All you had to do was look at the hot block and the change in temperature from one time to the next time. So whatever temperature increase resulted, you just say Q is equal to MCP delta temperature, and for the power, just divide by the time. So you're going to divide by the change in time over here. So MCP delta temperature divided by the change in time. Okay, so that gives me the change, or excuse me, the power going into the hot block from one time increment to the next. And then it was just divide them out. So the COP was the output energy divided by the input energy, which is that. Okay, but the subtracting off the MOSFET and the shunt resistor, that got a lot of people. A lot of people also they wanted to substitute in numbers for some reason, rather than just solve it symbolically and say, okay, now we put our data in, chug it out, here's the answer. Okay, and when people put the numbers in, I went, what data point is this for? And one data point doesn't even make any sense, because you have to go between two time periods to get the thermal power. So I was really confused on that. The better way to do it, in my opinion, is just do your math, get your graphs, and if you had just come over and done something like this, say, okay, there's my maximum, cool, done, end of story. That's the way I would have handled it. Instead, some people tried to back substitute values for when the maximum occurred, and it got weird. So then what I got for answers, up top here, this is my 12 volt run. Down here's my 5 volt run. And here's what I saw for COP results. 5 volts give you the best COP. Basically, you're sucking energy out of the cold block, but you're not creating a whole lot of resistance heating that you got to fight against. So you get a better COP. And there's your 12 volts right there. So A little bit counterintuitive, but you do the math and that's what falls out. Most people got that the 5 volt was better on COP, but I saw all kinds of wild numbers. Some people were saying that 12 volt always had a COP less than 1. Well, no, that's saying it's worse than just a piece of hot wire. So that should have been a giveaway. Some people said that the COP was like 7, 8, 9. No, that's above the theoretical limit. You're not going to get there either. So that should have been a giveaway. But somewhere in the 3s, yeah. And that's what I saw for cold climate heat pumps when I was an engineering manager actually doing the testing. We would see COPs of like 3, 4 using refrigerant 410A. And yeah, that's why heat pumps are a good deal. You know, you put in 1 unit of energy, you get 3 units of energy out. So pretty snazzy. Any questions on the lab, folks? I thought it was relatively straightforward, but I did catch a bunch of people. Okay. Moving right along then. So I think what we'll do is, I was going to drag you into the lab, play with this, and do an in-class demonstration. It's too cold out. Not going to be that cold. So let's just do it by video. Okay, so back when I was talking about sonic flow, one of the things I went over was critical pressure. When you hit Mach 1 at the narrowest point of a flow channel, you become sonically choked. And regardless of how much you lower the downstream pressure, you do not flow any more material. Okay, so we're going to demonstrate that. I got a flow meter right here. I've got the upstream pressure on this gauge. I've got my little restriction right in there. This is the downstream pressure. And this is an eductor, which is going to take compressed air, and it's going to make vacuum out of it. Basically, I'm just going to blow a high velocity jet into this T. I'm going to mix it with all the air that's in there. That's going to drag air in this direction, and it all comes out the entrainment tube. Hey students, I want to do a little experiment for you today. What I'd like to do is create Mach 1 or sonic choked flow right at that restriction. The equipment attached to this machine is a flow meter right here. So this is going to measure the flow rate going through that restriction. We've got an upstream vacuum gauge. This is going to measure the vacuum on this side of the restriction. Same vacuum gauge on the downstream side. So this will be the low pressure system. And just so you know, this is a highly calibrated cement block. Over here, we've got an eductor. This is going to create vacuum. We're going to use compressed air coming up through the center tube. It mixes with the air in this T and gets dragged along and pushed out through this brass entrainment tube. Okay, so let's see what happens. I'll turn the air on. And I've got flow going through. So I'm at 0.1 on my flow meter, and I still don't even have any real vacuum forming yet on the downstream side. Everything is just flowing right through. Still at atmospheric pressure on the upstream. Okay, let's turn up the vacuum a little more. Bring it up, say, to 2.5 inches of mercury suction. Still atmospheric on the upstream, but we're all the way up to 0.45 on the flow. So I will write that down. it up some more. There's 5 inches of mercury. Still haven't lifted off. We're still at atmospheric pressure upstream. And on the flow meter, we're up to 0.55. This is actually a water flow meter, not an air flow meter. That's why I'm not giving you units on that. But it doesn't matter, because it's all going to be just relative to 7.5 inches of mercury. And we're only up to 0.65 now. We've left the 10. We're at 10 inches of mercury suction. Still atmospheric. We've only got up to 0.7 now. There's 12.5 inches of mercury. Still atmospheric. And I'm still, we're just near over 0.7. How high we go. Seems like a really attenuated volume, because that was loud in the shop. Looks like about 14 is the best I'm going to do. And I'm still right at 0.71. So I now have sonic choke flow right at that restriction, moving Mach 1. And no matter how much I bring this pressure down, I will not get any more flow going through this device. Because I'm choked right here at the narrowest point. Okay, now future me is going to go grab this, you can actually see the trend. Okay, thank you, Pastor Pete. So,
You're not a child, you're a man. So stop wearing so many layers to go outside. And get the bearskin tactical hoodie.
my goal is to be as childish as I can be as long as possible. Alright, so, what Pastor Pete did is right on the screen. So here's all the numbers I was writing down. So there's the suction in inches of mercury. There's the flow meter. Suction pressure in PSI. And here is the pressure ratio across the orifice. So basically, the downstream pressure divided by the upstream pressure. And if you remember from the compressible gas lecture, whenever we go below 0.528, basically when the downstream pressure is half of the upstream pressure, we go supersonic, or we go sonic, and we choke. And lo and behold, the best suction I could do just with the limits of the equipment was 0.468. And look at that. So I was getting no more flow, even as my suction was increasing. And if I had better instrumentation other than my dial gauges, that's really close to 0.52, 0.53. Okay. So that's why I know that that is sonic choke condition. I suspect that the upstream pressure was just slightly lower, so yeah, I think that's off by a hair, but not much. Enough to say, yes, in fact, it does actually work. And my readings were not perfect right here on the low end. So if you need to push an orifice, you can always push it on the upstream, but you cannot push it any harder by lowering the downstream pressure. You'll get choke flow. So let's see. That's about it for the material for today. As I told you, you are going to do a rewrite on one of your lab reports. It's going to be due on 2/12, last day of classes. I have, I think, 4 more reports I got to get out, and then everybody will have their heat pump lab back. Try to get those done today, certainly by tomorrow. Let's see, what else? Please do your course evals. So go ahead and write that I'm a horrible, tough grader, and you didn't know which end was up, and you know, all the other stuff you guys always write about me. That's cool. Go ahead and put it down. Seriously though, I do read them, I do take them to heart. Anything that's constructive, I absolutely do integrate. If you guys want to come in my office and say, this was the worst course I ever took, and you got a constructive way to change it and make it better, wholeheartedly do it. Come tell me it was terrible, and I will do my best to fix it. Okay? Other than that, if there are no questions, we're good to go here. So we will do, there's obviously no lab next week. I'm going to try and replicate the most important lecture I saw when I was a student next week. So I had this tremendous tremendous lecture that a prof did impromptu, and I'm going to try and give that to you guys. So we're going to go lift my GTO. All right, that's it.